Hey friends, my name is Miss Mangan. I teach physics here at BHS, she, her pronouns. You either just finished or are currently working through the circuits unit, and we want to take a little bit of an asynchronous tangential um, uh, look into how does electricity actually get into your homes? Because what happens in a circuit is great, but where does our actual electrical energy come from? Which is, of course, way higher voltage and way more carries way more energy than the small circuits we're building in class. So the goal of this slide deck right here is to learn a little bit about where does our electric energy come from. And so you might have seen in a circuit, of course, that the energy comes here from the battery. Well, batteries are a form of chemical potential energy, which then is turning into electrical energy, which then in the light bulb goes into radiant and thermal energy. So we know that there can't just be large batteries somewhere in, like far away that is powering the circuits in our home. The reason that can't be possible is because one, we know that batteries, as they run out, they get dimmer, but our light bulbs are never ever getting dimmer. So, and when you try to make battery energy go farther and farther and farther, they actually become less and less potent. It sort of like loses energy to the wires along the way. And so there's actually a way more clever way than this kind of current. There's a way more clever way that electrical energy gets to our homes, which we're going to learn a little bit more about here. So you might have heard of this before. You might have said, oh, well, energy comes from oil or from coal or from nuclear or natural gas or solar energy or biomass. You might have heard that electric energy comes from these renewable and non-renewable sources of energy. And that's true. But the real question is like, how do you convert those forms of energy from oil into electricity or from coal into electricity? There's actually a really interesting but complicated process that we're going to look at right now. So here's what happens inside a power plant. And what you're going to see is on the left side, coal coming in. Coal is the most common power plant here in the United States. Coal is a non-renewable source of energy. We dig up coal from the ground. And over here on the right side, you're going to see it turning into electrical energy. But what's interesting is what happens in the middle. Take a look.
Coal-fired plants transform coal into electricity by pulverizing it and burning it in a furnace. The burning coal heats water in a boiler and turns it to steam. The steam, under tremendous pressure and at high temperature, provides the force to turn the turbine blades. The turbine spins an electromagnet inside copper coils in the generator, and that produces the flow of electrons called electricity.
Okay, so let's take a look at each one of those steps a little more closely. So first off, take a look at this flow chart. Essentially what they were saying in that video is that you start with some sort of fuel. They were starting with coal as the type of fuel, which of course stores chemical potential energy. They then heated that chemical potential energy, burned it until it boiled some water. By turning that chemical energy into thermal energy, they could boil water to make steam. Why make steam? Well, it's steam's kinetic energy that then can turn a turbine. And what that does is, we're going to look at this a lot more closely in the next couple slides, is that kinetic energy is moving crazy, crazy fast. It turns a turbine super, super fast, which they said turns some magnets. This whole process is called a generator, which then generates electrical energy, turning that movement of magnets into the motion of electrons, electrical energy in wires. And so looking at this whole process, you basically took coal, which is a stored form of potential energy, chemical energy, heated that to thermal energy, used that thermal energy to boil water. You might even think like, oh, wait, there's some phase energy in there. Totally true. That thermal energy boils water to make steam. Steam is moving incredibly fast, so steam's kinetic energy then turns into electrical energy in the generator. So that process right there, that last step of kinetic energy turning magnets, That feels a little questionable to me. And I want to tell you that there's some really interesting, almost like physics magic happening in here. It's not magic, it's physics. But what's going on here to actually make the electrical energy? This is where it gets really exciting. And Miss Kissel is going to tell us a little bit about what's going on with magnets and a coil of wire.
Hello. Have you ever wondered how a hand crank generator works? Well, I'm going to explain it to you. I'm going to explain it using this crazy setup here. So here we have a coil of wire. It's just a wire that goes around and around and around and around. It's connected to this device that's called a galvanometer. A galvanometer is something that measures current. And when there's current going through the coil, you'll see the needle move. If the needle moves in one direction, that means current's flowing one way. If the needle moves another way, that means current's flowing the other way. All right, watch what happens when I take couple of very tiny magnets and move them into this coil.
Oh,
Do you see the needle move?
woo!
I moved it pretty slowly. Watch what happens when I move the magnets more quickly. Oh, look at that. Now, so we see that the faster I move the magnets, the greater the amount of current created. Also, you should see that the needle moves in one direction when the magnets enter the coil, and they move another direction when I remove them from the coil. Now, I want you to notice what happens when I stop moving the magnets, but they're still inside. Nothing's happening. You should know why if you think about energy. Am I giving any energy to the system now? No. But when I move my hands, I am giving kinetic energy to the system.
I just want to be super clear what's happening here. There's no battery. This is literally just a coil of wire and a magnet. So this is a way to generate electricity, electrical energy in a coil of wire without using any battery at all. So there's something about the kinetic energy, the motion of the magnets here that is causing electrons in the wire to move.
All right, watch what happens now instead when I use a whole giant stack of super strong magnets. Whoa! All right, I'm going to go move them very slowly. Still, there's a decent amount of current being created. Whoa! And when I just place the super strong magnets inside, eventually the needle stops. So when we think about the energy here, my hand has kinetic energy. That kinetic energy is changed into electrical energy in the coil, and then it changes back into kinetic energy here in the galvanometer. The same thing happens with the hand crank generator. When you turn it, you are giving it kinetic energy. That kinetic energy changes into electrical, and that electrical goes to the light bulb and makes what kind? You know it, two kinds. Yes, that's correct. Radiant and a bit of thermal when it heats up. And what's actually inside here in the silver part that you can't see is a magnet and a coil of wire. So when I turn the crank, I'm moving a magnet in a coil of wire. And that's how a hand crank flashlight works.
So this whole thing is called electromagnetic induction. Take a minute, pause the video, and write this down in your notebook. Electromagnetic induction is what happens when you move a magnet. So movement of a magnet is, of course, kinetic energy, and that generates a current, aka electrical energy, in a coil of wire. So what's weird about that is that magnetic fields in motion can be used to generate an electric current. This is what's going on at the power plant, in the generator part of the power plant. So in this generator part, you've got steam, which has a huge amount of kinetic energy. It turns this turbine, and that turbine is over here connected to a huge magnet. And we're talking like crazy strong magnets with crazy big, like room-sized coils of wire. And when you take really, really strong magnets and room-sized coils of wire, you generate a huge amount of electric current. And that electric current then is connected in very, 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 very miles long wires to our buildings, very, very far away from the generator in the power plant itself. So I want to show you a little bit about what that looks like in using a simpler model so that we can see what's going on in the electrons inside the wire. Okay, so in this simulation, in this PhET simulation, what you'll notice is we've got a coil of wire, a light bulb, and inside this coil of wire, all these teeny tiny little blue electrons. This is just like the circuit simulation that you saw, with each one of these little tiny blue dots being an electron, which is just in the wire as it is. If I can pick up this magnet and give it some motion, some kinetic energy, you'll see that if I move this near the coil of wire, in and out, you see exactly what happens. It's a little laggy because I'm doing a video. You'll notice that exactly what Miss Kissel saw in the video happens here in the wire. But instead of hooking up the galvanometer to this, which I could have used this little galvanometer right here, which would make the current go backwards and forwards and backwards and forwards, we can also hook up a light bulb. So essentially what's happening here is I'm converting the kinetic energy into electrical energy, meaning motion current of the electrons in the wire. Now, what if, like, this is annoying though, because Miss Kissel had to like take this and move it constantly. What if there was a way to always cause motion in the electron or in the magnet that would always cause motion in the wires? And so check out this idea. What if we took a little bit of water and we put the magnet on a wheel, and we caused the water to constantly fall and turn the wheel? Now you can see that essentially the magnet would be in continual kinetic energy, in continual motion. So where's it getting its energy from? Well, it's getting its energy from the gravitational potential energy of the water. This is how an old school water wheel works. And this is also how current hydroelectric power works, is that we take one form of energy, gravitational potential energy of the water, we turn that into the kinetic energy of a magnet, and as long as we put that magnet near a coil of wire, it causes electrical motion of the light bulbs, of the electrons, and that causes radiant energy in the light bulb. So you can see a huge number of energy conversions here. Now, if you're really clever and you've been noticing that this current in the wire does not look like what we saw in our circuits unit. In our circuits unit, we saw electrons always moving one direction, from the battery through the light bulb and then back to the battery. But here, you'll notice that the current is moving backwards and forwards and backwards and forwards. And so that's causing the light bulb to go on and off and on and off. This is a new kind of current called alternating current. Alternating current is different than what we saw in circuits, which was called direct current. Direct current just moves the electrons in one direction. But here, because the magnet has two different sides, north and south, that's causing a flip of the motion of the electrons. Sometimes it's pulling them, sometimes it's pushing them. And so this motion allows current to actually flow really, really far away, miles away from the power plant itself. This whole picture that you see right here, this whole thing is called a generator. And again, inside a regular generator, steam is turning the magnet around these giant coils of wire, which then the coils of wire would go miles and miles and miles and connect to the two sides of the outlet in your house, and just wait for you to plug in on one side your light bulb or your refrigerator or your stove. And so this whole thing down here is what happens at the power plant. Up here, miles away, is what happens in your home. Okay, so put this in your notes. Alternating current. Alternating current is what it's called when electrons oscillate back and forth due to the motion of a changing magnetic field. So again, that's alternating current is different than direct current, which is what we saw in our circuits unit. Pause the slide deck if you need to. Okay, so going back to our power plant flow chart, again, coal power was one kind of chemical energy that we could turn into thermal energy, which turns into kinetic energy of the steam. The steam turns the magnets in the generator, which turns into electrical energy. But coal is not the only form of chemical energy we had. We saw lots of renewable and non-renewable sources of energy. So let's take a look at where some of those come into this flow chart. Natural gas, oil, and biomass are all different forms of chemical energy that can be burned to turn into thermal energy to boil water to make steam. But geothermal energy is actually a really clever renewable energy source, which uses the heat from the earth that then, therefore, it doesn't need to be boiled to make steam. It already is thermal energy, which can be directly turned into steam. And that steam can turn a magnet, which then makes electrical energy in a generator. Wind and hydroelectric power are ways of completely skipping steps 1 and 2 and going directly to kinetic energy. Wind power is already kinetic energy, and hydroelectric, that's water power, just like we saw in the PhET simulation, is already the motion of something, and that can directly turn magnets. So essentially, the generator is the most important part of this whole process, which is what is causing kinetic energy, sometimes that you need to get from chemical energy to thermal energy and then turn to kinetic energy and steam, or kinetic energy and wind, or kinetic energy and hydro. It's all about turning that kinetic energy into the motion of a magnet, which then turns it into electrical energy. And all of these steps have significant energy loss. So if you started with a whole bunch of coal, maybe only 40 to 60% of that coal's stored chemical energy actually gets captured and turned into thermal energy. And again, only 50% of that energy turns into kinetic. And again, only maybe 50 to 60% of that energy. So we're actually losing energy at each one of these steps. So the amount of energy we start with, if we started with like 100 joules of stored chemical energy in coal, only about 10% of that, right, 50% of 50% of 50%, only about 10% of that actually ends up as electrical energy at our home. And so that's one reason why geothermal, wind, and hydroelectric, which are all renewable sources of energy, are way better than coal or natural gas, is because there's fewer energy conversion steps at which energy is being lost. You might be noticing that there's a few types of renewable energy that are missing here, and they kind of break the mold from this path. One of them is radiant energy, and radiant energy in solar panels actually can directly go to electrical energy. And I want to tell you a little bit about how solar panels completely bypass a normal power plant flow chart. And nuclear energy, which we're going to be spending almost the entire rest of this asynchronous unit on. So let's look at radiant energy first. How does a solar panel work? Well, in a solar panel, we get radiant energy, and then there's some magic that happens here in the solar panel. And again, I'm going to show you that magic. It's not magic, it's science, that directly turns into electrical energy. And so what's so cool about how solar panels work is they take the radiant energy, which we know is an electromagnetic wave, and that goes directly into an atom. And that these are really specifically chosen atoms. They're very, very cool. You're going to learn more about these atoms in chemistry next year. And what they do is each one of the electrons in the atom absorbs a photon of light, absorbs that electromagnetic wave. And what happens is that electron leaves the atom. It breaks free from its atom. That's unusual. Electrons don't usually do that. But if we can capture this electron, check it out, that's electricity. So essentially what we've done here is we've absorbed radiant energy from the sun, write this down in your notebook, absorb radiant energy from the sun into the electron, cause that electron to have so much energy that it pulls away from its atom. And then if we can just catch that electrical energy, so here's the silicon that's in the solar panel. Those electrons, if we can capture them in a wire, which is exactly what we do, we can cause them to, let me move my face here. If we can capture those electrons in the wire, we can cause them to flow through a circuit and then flow back to the other side, the other type of silicon in the solar panel. And so that is a direct way to get radiant energy to turn into electrical energy. And that whole thing is called the photoelectric effect. Photo, because a photon of light turns directly into electron energy in a solar panel. The other thing that's kind of breaking our mold of power plants back here is nuclear energy. And nuclear energy is a different way to store energy that's not chemical potential energy. You can see that it still uses the same thermal energy to kinetic energy through a generator making electrical energy process, but nuclear energy is crazy powerful, and I want to tell you about why. So a nuclear power plant looks very similar to the other coal power plant that we just looked at. There's still a place where steam is generated. That steam turns a turbine, which turns the magnets in a generator to generate electrical energy. And the only big difference here is what's happening in the reactor vessel. You'll remember in the old one, coal had to be constantly fed into here. Inside of a nuclear reactor, there are these teeny tiny little pellets that are made of uranium. And what's going on inside this nuclear reactor is really what's happening, not even in the uranium atoms themselves, but inside here, if you blow it up, a uranium nucleus has some really intense energy stored inside of it. And throughout the rest of this unit, we're going to tell you about like how exactly you get the energy out of a nucleus. But preview, basically what happens is you take a neutron and you blast that uranium nucleus into two pieces. It falls apart into two pieces and a huge amount of energy comes out. What does that energy do? Just does the same thing other energy does in a coal power plant. It heats up some water, boils that water into steam. The steam has a lot of kinetic energy. It turns a turbine, makes electrical energy in a generator. But the ability to take the energy out of the nucleus of an atom is something that came much, much later, and we learned to be incredibly powerful. So you'll see that actually one teeny tiny uranium fuel pellet, which is the size of your fingertip, has as much energy as a ton of coal, 149 gallons of oil, and 17,000 cubic feet of natural gas. So all three of these forms of energy, not only do you need a huge amount of them to get out the same amount of energy, but each of these is a non-renewable source of energy, meaning that it creates, that it gets used up, and also are going to generate greenhouse gases, which are terrible and pollutive for our environment. So one thing that is really, really powerful and that we're going to learn a lot more about is the amazing reaction, the nuclear reaction that's happening inside these uranium fuel pellets that can store and therefore generate much more energy than a traditional power plant does.